So welcome to lecture 8 of MCS 471, numerical analysis. Today we will consider linear algebra. So the title is Introduction to Linear Algebra. In a way, there will be very little numerical analysis in this lecture. And as the title says, the purpose of this lecture is to introduce some important notations and algorithms in linear algebra. So why this lecture? So there is, of course, a course in an entire course in applied linear algebra, but this course is not a formal prerequisite for this course. So that's why this lecture is here, to make sure that everybody enrolled in the class is a little bit on the same page. And also, even if it would be a formal prerequisite, even if an applied linear algebra course or a linear algebra course would be a formal prerequisite, it would then still be very useful to introduce the algorithmic aspect of the topic. So we will see that matrix notation is extremely important. And actually, the second part of this lecture will formulate a row reduction in the matrix notation. So we will introduce the LU factorization with what is known as the Doolittle algorithm. So notice spelled with two O's. This is we will certainly do a lot in this lecture. So the essence is actually that we work with matrices, unlike working with equations. So I should have said that what is one of the main problems in linear algebra is solving linear systems. We will first see that triangular linear systems can be solved easier, and the LU factorization will reduce any general linear system into the upper triangular and lower triangular form. So, okay, so the main background here is mathematical, and we always start with notations. So in a first linear algebra course, one may have started from looking at equations, but here the main actors are the matrices and the vectors. So we start by introducing them properly. So a matrix is a table of numbers with a number of rows and a number of columns. In this lecture, the number of rows and the number of columns, the N and the M here, you can assume that they are the same, but later in the course we will look for more systems and more equations and more unknowns. So a vector is a special matrix, but so we kind of write it differently. We write it with a bold notation. Matrices are typically written in uppercase, with uppercase letters, to distinguish the lowercase letters, which are then the numbers. So the numbers in the table have a double index. So working with double loops and even triple loops is actually quite important sometimes. All the numbers are by default real in this lecture. By real, I mean the real, not the floating point numbers. So we will, in later lectures, see that in practice, the linear algebra is quite, on mathematics, is quite different from the numerical linear algebra. What can we do with matrices? Well, we can multiply matrices with a number. We call that the scalar multiplication. We can add two matrices. Two matrices if they are of the same dimensions, if they have the same n and the same m. Then the most important operation is the matrix multiplication. And this is where the triple loops come in. The result of a matrix multiplication is again a matrix. So that is already a double loop if you want to enumerate all the elements. But here you see that in the definition of the element in the matrix product, we have another loop. So big sigmas in computer science, they are translated immediately as loops. So the matrix multiplication is an algorithm, is an operation that for full matrices, so if all the elements are different from zero, and don't have any specific patterns either. So that is an operation that will be cubic in the dimension. Of course, dimension, now there are three numbers. So it's even a little bit more complicated than addition and subtraction. So the number of columns of A must match the number of rows in B. So you have this M here that is shared between the matrix A and the matrix B. And you see the M kind of disappears in the C, but the M actually plays then again the critical role when you make the numbers. So doing the matrix multiplication efficiently is a very critical operation, both in software and both in theoretical computer science. So we will write things in matrix notation. So we can, in shorthand, we can write a multiplication simply with a star, but the star is different from the star of multiplication of numbers. So you can look into any linear algebra textbook and look for examples where the product of A with B is not equal to B minus A. So that is the first exercise. Now you can also do this, of course, it's recommended that you do this with software, generate two random matrices and multiply them. So actually multiply them A times B and B times A. The next exercise is actually a bit more interesting. So this is not a pure mathematical proof course, but exercise 2 actually asks for a proof. Although you can also get to it by doing a lot of experimentation and actually reasoning about the algorithm itself. Exercise 2 invites you to look at the formula for the matrix multiplication. I can write the formula here. So we are multiplying A. So we have the I index, and then we have the running K index, and we multiply this with the elements on the kth row. So K is the running index. So this is the ijth element. Now what it means to be an upper triangular matrix is that all the elements that are below the diagonal, so if the row index starts to be larger than the column index, then the element is 0. So if we multiply here, if we apply this here, you can restrict, in a way, this also has a practical, so we are computing these ijth elements. So if we do this computation, we can actually save half of the operations. And in computer science and asymptotic cost analysis, we only care about the exponent. But in real computations, if you can do something twice as fast, then actually this is often a big thing. So in a way, exercise 2 is a mathematical exercise, but you can also see this as a better way to find a better formula in case your matrices are upper triangular. So you can work, if you want to show this, there are many ways to show this. You can work with the formulas for Cij. So what will actually come out of this is that whenever you are multiplying with 0, that's a term that you can ignore in the summation. So in starting the proof of this exercise, you start by stating what needs to be done. And that's actually changing the definition, saying that the matrix C, which is the product of two upper triangular matrices A and B, is upper triangular. And that means this, what you have to prove here. And you can first prove this by example, and then see that your arguments actually generalize for any dimensions. All right, where do the linear systems now come in, and how will we write linear systems? So we can do this as equations, as you would do in symbolic computation, or if you would do this on paper. But even if you would do this on paper, the matrix formulation has a much neater way of representing, in the sense that you can separate very clearly what is known and what is unknown. So the mx values are the unknowns, the coefficient matrix and the right-hand side vector are the inputs. Notice this is again illustration of a specific case of matrix-matrix multiplication. The second matrix, the matrix-matrix multiplication, is a vector. So the number of columns of the first matrix A equals the number of rows in our vector. So it's another check. And actually you can go from the equations to the matrix form, but you can also go back. So in a way, why is this symbolic? You can see the linear system in equation form as a symbolic representation of the formulas for the matrix vector multiplication. So then actually you look at this matrix form, read it from right to left. Actually, you say that B equals A times X. Instead of saying A times X equals B, which is the matrix equation, if you look at the formulas for the algorithm for the matrix vector multiplication, you look at the formulas as you would see them if you performed the matrix vector multiplication. So, of course, the short method that we can write and say things. So the shorthand notation of a linear system is then simply denoted by A times X equals B. And to make the distinction that X and B are not numbers, but vectors, we actually write them in bold. So this notation is extremely convenient, certainly when the number of equations and the number of variables actually increase. You do not want to write everything down. All right, how do we solve linear systems? Well, first look at a very specific case. Let's look at upper triangular linear systems. So upper triangular matrices, everything that is below the diagonal. So here is the diagonal. So these are the elements for which the row index equals the column index. Everything below the diagonal is 0. So these are very special matrices, and the linear system then can be solved by what we call back substitution. So we look at the system from bottom to top. So the first equation that we can solve rather easily is the last equation. And we can solve it if the diagonal elements are non-zero. So you see that we have 3 equations and 3 unknowns, and we do this in 3 steps. So if we can do this for 3 equations and 3 unknowns, then you can see the pattern emerging to write down the general algorithm. So in a way, this is not really a programming class, but I hope that you can see how the formulas translate into algorithms. So one has one loop here, so the loop is indicated here by the arrow going up, and you have another loop that actually makes the multiplication of 2 vectors. So the formulas are written out in full, but you could say that this algorithm to solve an upper triangular linear system can be translated in a sequence of multiplication of vectors by vectors, so what they call the inner product. And the vectors get longer and longer. So there's actually nothing that gets multiplied here in the numerator in the first step. Here you have only 2 numbers, so we actually don't see the vector. And here actually we do multiply 2 vectors. So the vector that is defined by this first row here, except the diagonal element. So we first spell everything out, and then we try to see things in a shorter way. So I mentioned the double loops. So solving an upper triangular linear system, it looked like matrix. It looks like you cannot do it faster than matrix multiplication, but you can. So this is actually now a much faster algorithm than matrix multiplication. All right, here we have the general back substitution formulas. It's good to write them out in full because it makes you think about the indices. These formulas are kind of the transition from they're actually the transition into the algorithm. So on the next slide, we actually will write down the pseudocode formulation. So this is the first algorithm we see. The algorithm is defined twice. So here you see the algorithm defined in symbolic form. In the ... notation, that then gets replaced by for loops. For loops in pseudocode, where we leave off the end. When we go to Julia, one should not forget the end. Every algorithm starts with the input-output specification, where we specifically state the condition that needs to be satisfied, the precondition, essentially, if you like. So all diagonal elements need to be different from 0. In this lecture, equal 0, not equal 0 is a very sharp distinction. In numerical linear algebra, that that distinction is very critical, but not for this lecture now. So this algorithm is correct as long as all the diagonal elements are different from 0. All right. What is now the cost of this algorithm? So the cost is quadratic in the dimension. So the parameter, the main parameter is the number of equations and the number of variables. We are computing n numbers, but we can do this with a number of operations that is quadratic. Now, not every number requires the same number of operations. So the last number is just computed. The last coefficient is computed by just one division. One needs to do a lot more work for computing the first number. So if you want to check correctness real quick for a back substitution, check the first number. Because that's the number that is actually involved in most of the operations. Again, we are already doing some numerical analysis. I can't refrain myself from actually doing it. But this cost analysis actually has also the practical consequence. So symbolically, we can see the algorithm as working out the formulas. Numerically, we are interested not only in the cost, but also in the accuracy. So typically, the number that will be subject to most errors will be the number that goes through a lot of operations. And actually here, if we count the number of operations, then how you should read these lines here? Well, for the last element, we do one operation. So we count the number of floating point operations. So the fact that we are adding to I, so we are decrementing I, so I goes down and J goes up. We do not count these operations. We only count the floating point operations. Or here in this lecture, we count the operations on the real numbers, not on the integer numbers. So the way to read this here is that every line expresses the cost that is required for one number in the solution vector. So the first number requires n minus 1 operations. And actually, number of operations, I see now that it should be the number of steps. Because as you can see, we count, here we have one multiplication, one subtraction. So actually, it should be multiplied by 2 for the number of operations. But the point is, if you make the sum here, you get a quadratic cost. So we have the n square that is getting up. It's divided by 2. But then it gets multiplied by 2 again. So we have an n square number of operations. And here it's spelled a little bit better out. So we have the number of subtractions and the number of multiplications and the number of divisions. We have our first theorem. So if we have an upper triangular system of n equations in n unknowns, then we can solve this at a cost which grows quadratically in the dimension. Which means that if you double the dimension, then the expected time will quadruple. So you will have to wait 4 times longer. Not as good as linear quadratic. So from your data structures or from your algorithms course, you may remember that quadratic sorts are inferior. So this puts also a bound on the practical dimensions of the problem that we can solve. But it is much better than matrix multiplication. All right. So now the next sequence of the next series of 3 exercises asks you to redo everything now, but now for lower triangular matrices. So in a way, lower triangular matrices are a little bit simpler because you can think forwardly. So your loops actually go in the nice natural way. So here we are looking for formulas and then for an algorithm. You can write this algorithm up in pseudocode. So you can, these are 3 paper and pencil algorithms, exercises. But of course, writing this up in the Julia notation is so much nicer. You have also a check on the correctness of your work. Now, the cost of solving a lower triangular system of equations is also quadratic. And the same arguments are applying to the same as the ones that we had for the upper triangular matrices. So it's called forward substitution. Here is how you can verify this in Julia. Julia provides us with a very nice mechanism to compute interactively with matrices, just as we would with numbers. And here is the shorthand notation for the solver. In a way, this is kind of an odd slide, but a very practical slide. If you ever have to solve linear systems, please use the backslash operator. So the backslash operator is a shorthand notation for a linear system solver. And what this slide shows is that if you are having the system A times, so here we have A times X equals B, then this is here verified. So we make random matrix or random vector, and if we do the matrix vector multiplication, where the vector is the outcome of the backslash, again, it's not the division operator, please don't confuse it with that, then actually you have the exact right hand side here. So we have the random right hand side, which also shows up. So that's another way. If you are coding up your own lower triangular system solver and you want to check it, well, check it on the backslash operator. All right, there is a little bit of numerical linear algebra here. We see that it is 0, but notice that the default printing in Julia was not with scientific notation and not to the full precision. So we will go much deeper into on Monday. So when we get to numerical linear algebra, but there are norms. So we touched very briefly on norms when we talked about the size of a polynomial defined by a coefficient vector. Well, here is the norm of a vector, which we will call the backward error. So the quantity that it's computed here will be known as the backward error or the residual. Is the linear algebra module that is already standard installed in Julia. So linear algebra is so fundamental to scientific computing that as a language it is actually inside Julia. All right, so that was the first part, the first important part. So we have seen the matrix notation and how to solve triangular linear systems. How do we now solve general linear systems? Well, we will reduce them to an upper triangular form. So even if you have not taken any formal linear algebra course, you must have seen the algorithm, the row reduction. And what is very specific here, what we will do in the remaining 20 minutes, is to rewrite the row reduction into a matrix notation. So we will see that everything can be reduced to matrix multiplication. Here is the formal description of the input-output stage. So we want to bring any general linear system, we want to reduce it to an upper triangular form. So one can see this again as a rewriting exercise from symbolic computation, but here we rewrite it into our matrix notation. We will also rewrite in the process the right-hand side. So everything will now be written in a matrix notation. So let's do the example of row reduction, and let's do it extremely slowly. So we have the simplest matrix we can think of, 1, 2, 3, 4, and let's reduce this to an upper triangular matrix. So what we do is we will make this element here 0, and we can just make it 0, just write that 0. But wait, not so fast here. We want a matrix that has the same solution if it is the coefficient matrix of a linear system. So saying, hey, why can't you just put zeros in there? No, we actually want that the equations are equivalent. So in a way, mathematically, we do something. There is an invariant here that holds when we do this rewriting. The invariant being that the matrix, as seen as a matrix of a linear system, the upper triangular system, the x will still be the same. So I should have pointed this out at the previous slide, so I forgot this. Let me back up a little bit. So the point is, of course, the matrix notation, but the mathematical point is that in this reduction process, what changes is the a into the u and the b into the y, but what doesn't change is the x. So that is the invariant. We just don't introduce zeros by turning things into zeros. So the important thing is that we do linear combinations of the equations. And that is written down formally as a matrix. So intermediately, we have the formal notation of what you will say in words. So if you have to teach somebody how to make an equivalent linear equation, then what you will do is you will eliminate by taking the coefficients on the second row and subtract 3 times the coefficients on the first row with this. So notice that this is again a vector operation. So we are here, as is written here, we do here an operation of 2 vectors, a scalar multiplication and a subtraction. So that gives us the upper triangular matrix. But now actually notice that you can rewrite this operation as a matrix multiplication. So we have the matrix, which is now lower triangular. That is lower triangular and has the multiplier on its lower diagonal. It's at the same spot as where we are going to introduce the 0. So this seems rather cumbersome and far-fetched, and indeed for a 2x2 linear system, one would not do this because it's simply too little. But once dimensions increase, this has an extremely beneficial effect. Also, we will see that this can also be used. So the property here is that the lower triangular matrices with ones on the diagonal, or any triangular matrix that has non-zero diagonals, is actually invertible. So we can undo the multiplication. So in a way, these type of matrices are actually quite easy to invert. And solving is also sometimes seen as matrix inversion, which is also a complicated operation. But with these multiplication matrices, these multiplier matrices, things get easier. All right, so then we get to the LU factorization. So we will rewrite a matrix as a product of a lower triangular with an upper triangular matrix. And that factorization is known as the LU factorization. So the LU factorization is very important for the solving of a linear system. That is explained here in the application. So once one has the factorization, that then the solving of the linear system is reduced to solving an upper triangular system. So we actually do this at the last step. I'm sorry, we do this in this step. So in the third step is something that we started with in the first part of this lecture. Here, this step is the exercise. So the LU factorization reduces linear system solving to the solving of triangular systems. That is the importance of the LU factorization. An application is the computation of determinants. So determinants, if you have to compute them, then actually you can compute them also with an LU factorization. You can just compute the LU factor, the determinants of the upper triangular matrices than just by making the products of the elements on the diagonal. And why is the determinant important? Well, it gives you a criterion for when your LU factorization is valid. So I skipped over that at the previous slide. So when you define something, you also have to wonder yourself, does this actually make sense? Can you always write a factorization like that? Yes, you can, if and only if the determinant is different from 0. So the determinant is a property of a matrix that is independent on how you compute this. So here we introduce the determinant as an application of the LU factorization. So in some sense, it seems like you can only verify that you can compute that an LU factorization exists if you compute it. But take this from me, so this property is a general property, independently from how you compute it. So there is an after the fact verification that gives a condition for the LU factorization to exist. All right, the exercises in this lecture are paper and pencil exercises, which is kind of unusual for this course. Computations, long computations by hand, we actually are not doing it. You can use a computer algebra system to do this. So we have seen SymPy is actually quite good for this, for exact rational arithmetic. Doing this still makes a lot of sense if we really need to verify the numerical results. So this gives us an absolute way of doing this, other than actually making up a linear system where we know the solution. All right. Now we get to the algorithm, which is attributed to Doodle. I will derive the algorithm by formulas. So we are now again doing the matrix multiplication. So in a way, if this matrix notation is still kind of unfamiliar to you, so here's another opportunity to get familiar with it. And it's also multiplying matrices where there are a lot of zeros in there. So in a way, it's a little bit Doolittle. We don't have to go all the way. So you can then see what allows me here to illustrate that actually we do the row by column multiplication. So this is this element. So, and this kind of explains why, for example, this very first column here, let me write it in green. So here we have only one, the formulas are extremely simple here because these formulas are for the first column. And all the elements here on the first column of the product are obtained by making the first product with the first column of the U matrix. And that first column has a lot of zeros. So that's actually the least expensive column to compute. And you can also kind of see now from this matrix product how actually we can compute the LU factorization column by column. So the first column with the multipliers, actually you only need, so once you have the U11, you can actually then immediately compute the two multipliers. So here is the algorithm, but not with loops, but with explicit formulas. So notice now we see these formulas as now as an equality between two matrices. The matrix at the left with the known numbers we know, and then we have the matrices at the numbers at the right, the L's and the U's we don't know. But notice that if you know U11, and U11 is just a copy, then actually the numbers L21, L31 are actually just obtained by division. And you can see how the column-wise computation of this LU factorization makes a lot of sense. Which, if you think about this in the equation way, is actually not making that much sense. But from an algorithmic perspective, with the matrix notation, it actually makes a lot of sense to see it that way. Now, from the formulas, we get to the loops. So I'm hoping that I didn't use the ... in the algorithm. So you are a little bit, I'm running a little bit low on time, but if you are a little bit, if this goes fast now, from the formulas to the for loops, do one case with a 4x4 matrix. And then again, SymPy is extremely useful here. You can do this all symbolically. MCS 320 is actually on the track, on the computational track, and with symbolic computation, you can verify these formulas. What is important here is the triple nested loop, and actually I should now indicate this in red, because this has an important consequence on the cost. So the cost intuitively will be cubic in the dimension, and that's you can kind of intuitively see because of the nested loops. All right, so we can now immediately go to a function in Julia. So in a way, and I guess that this is also very useful for the first computer project that is due next week. Making for loops, if you have to make tables, are very natural. So here you see the syntax in Julia for making for loops. Don't forget the end. So here I have one major loop, so that runs over the columns of the matrix. And we then have two inner loops that run over the rows. So this is in a way a symbolic algorithm or a mathematical algorithm where we are returning the lower and the upper triangular matrices as the L and the U mathematically. Here we have the lower and upper triangular matrices. You can verify formally that when you do here the low and the up, they are the output, but it's interesting to actually to see that the K here never exceeds the I, and the I never exceeds the J. So the K stops with I minus 1, and the largest value for I is actually J. So you will only use known quantities when you go over this algorithm. So if you want to verify that when you are computing new elements of the low and the up, you will never use values that you haven't computed yet. So this is not a recursive algorithm, I want to say here. All right, so this will give us the function. This gives us a function to verify that we can actually, for a random matrix, a general matrix, where the determinant is not 0, where we can decompose that matrix as a product of a lower and an upper triangular matrix. So this is the mathematical algorithm. It is mathematically correct as long as the determinant is not 0. It is not a good numerical algorithm. Now I will say in the last 2 minutes something about the costs. So the argument is explained over here with the explicit counting of the number of steps in the innermost loop, and then assembling this. So we look at the innermost loop here, where we get the same number of steps as we did with the back substitution. So in some sense, this proof goes way too quick, but keep in mind that we have done the back substitution very carefully. So we are using the same arguments here. All right, I do not want to go over time. Let me summarize the main theoretical results here. The cost of LU factorization is just the same as the cost of matrix multiplication. Once you have an LU factorization, if you have to solve many linear systems with the same coefficient vector, but with a lot of right-hand sides, a lot of different right-hand sides, then this formalism actually pays off. So you actually save the expensive step of computing the L and the U. So in a practical manner, if you have to solve many linear systems with the same coefficient matrix, then this is a recommended practice. All right, how do we verify this with Julia? So Julia actually does have a built-in LU, and that's again the recommended to use. We make a system that has a specified solution, so we know the solution 1, 1, so we can verify. And the session continues. So the purpose of these remaining slides is to see how to use Julia calculator. Calculate with matrices and vectors as you would with numbers. All right, then, so I mentioned the inverse, and here's the application of solving a lot of systems with different right-hand sides. And the right-hand sides are the columns of the identity matrix. So computing inverse is this matrix equation, and one can do this efficiently when one stores the L and the U of the LU factorization. So this concludes this linear algebra lecture. We will see a lot more linear algebra, but this lecture had to focus on the linear algebra.